This is Mr. Sitta again, and I'm going to show you some different. Um, I'll show you some different charts that I've posted, and I'm not sure if this one. Yeah, I think that one holds up. Okay, this is a breakdown for intermolecular forces. Okay, so interacting molecules. The questions you would ask: are there ions involved? If that answer is a yes, okay, then you can say, are there polar molecules present with the ions? If the answer is no, then out here, this is strictly ionic bonding. That's salts, okay? Um, if you have a salt in water, something polar, that's your ion dipole. These are not considered to be intermolecular forces out here, but they are important. It does talk about ion dipole forces, forces between salts and water, and just the force between the salt itself. On the left, these are our intermolecular forces, because if they're not ions, then they're molecules. And then you're just asking yourself, are your molecules polar, yes or no? If the answer is no, then that's dispersion forces. This is LDF, which is a van der Waals force. And this little chart seems to disagree with Professor Dave. He says van der Waals forces, which I like. That name van der Waals, I say they're wonderful forces, because I would have to believe that van der Waals means wonderful if you're Dutch. But I always say they're wonderful forces. This says, yes, dipole is also van der Waals force. I usually say they're all van der Waals forces. To me, van der Waals forces are just intermolecular forces. But I guess I'm a little more out here than Professor Dave. Okay, then are hydrogen bonds involved? If you have N, O, and F connected to H, that's a special case of hydrogen bonding. Now that's hugely important, because that's important in biology. That's important in life. That's what holds your DNA together. Your DNA is held together by hydrogen bonding. It's important in proteins. Hydrogen bonding, it's just such an important factor in life that's a biggie to know. Okay, well, if you're not hydrogen bonded, then you're just a dipole. So this is just a quick breakdown of that. Now, I have a couple that are a little more. I like this one. These are all on my website. This gives you more of a molecular view of it. Okay, hydrogen bondings, OH, FH, NH, extremely strong. Now, here's something I'll say. If I'm looking at a water molecule, okay, this is a covalent bond between the O and the H. This is approximately like 400, I'll just say 450 kJs per mole. Well, a hydrogen bond is between two adjacent water molecules. So the hydrogen bond is between this H and this O. It's kind of an electrostatic charge that just exists between here. It's not a real bond. It's not a shared pair of electrons. But compared to that 450 kJs per mole, hydrogen bonding is around 4 kJs per mole. That's huge. Breaking this bond would be like breaking a diamond, okay? Because a diamond's 100% covalent bonding. So that'd be like you trying to dive into a diamond from in a swimming pool. This is you diving into a swimming pool. The water would give way, and I guess if you take your hand and you go into the water slow, it goes in easy. If it's an impact, this is more physics. But if you did a belly flop, the water becomes like concrete to you. So if you hit it real fast, that hydrogen bonding can kill you. Because if you jumped off a high object, you hitting the water would be like you hitting concrete, and that just has to do with the impact momentum. But I won't get into that. Okay, extremely polar. These are the strongest of the intermolecular forces. Dipole. You have two polar molecules. A good example would be HCl. Hydrochloric acid would be highly polarized. The chlorines would have the electrons. Medium strength. They're stronger when the molecules are closer together. LDF is in everything. Now, what's confusing to a lot of people is if you're a dipole, you still have LDF. There's still LDF in something with a dipole. If you have hydrogen bonding, you still have LDF. So LDF is in everything. It's the ability to polarize momentarily. It means the electrons can shift to one side of it. When they do, they induce they polarize. They become, the more electrons you are, the more likely you are to polarize. Well, if suddenly this is a positive, it pulls the electrons in this one next to it. So that's called an induced dipole. So again, we normally would think of this happening in things that are nonpolar. Well, for a second, every nonpolar thing can become polar. It's in all atoms and molecules. It's the weakest force, and it increases in strength as the molar mass increases, but it's really the number of electrons. Okay, and then one thing I'll say about LDF, with shape, if you have a long molecule that's like a rod, consider like a can of worms, that there's a lot of areas for attraction. And if the worms were round, that force of attraction would have, like, if you poured these out, your worms would have a high viscosity, like a can of spaghetti. Well, this would be like SpaghettiOs. If they're round, you have less attraction. So the shape of the molecule can change your LDF. Okay, so it's molar mass and shape for this one. Okay, whether it has a lot of contact area or short contact area. And before I explain that in gasoline, talking about gasoline, I always like to talk about gasoline. Oil would be like having your can of worms. Your oil molecules are very long chain, and diesel fuel, if you get the normal gasoline's like C5, diesel fuels like cetanes, they say C12. If you get up to like C18, you're talking about oil-like molecules. Well, in your engine, as you run a car, these bonds break. As these bonds break, your chains become shorter and your viscosity, your thickness of your oil decreases. So it's not able to protect your engine. And that's why if you have an engine, you should be changing oil like every 6,000 miles, because the viscosity drops with time. Okay, so that's one aspect where they actually show you a commercial and they tell you to change your oil, and they're actually giving you good advice. Because if you don't, you can end up ruining your car, and a car engine could cost you about $8,000 to replace, maybe $4,000 to $8,000. You don't want to ruin a car engine. Okay, I printed these out for you. Just go through this one. This is crystalline solids. Okay, just talking about solids, there's 3 types of forces. One is molecular. If I have 2 molecules, okay, these are your van der Waals forces: London dispersion, dipole-dipole, or hydrogen bonding. Okay, these are fairly soft to low. You can have a high melting point, low melting point. Poor conductors of electricity. Okay, so this would be molecular solids. An example of a molecular solid would be like butter. Okay, you get all that it's fairly soft. Other molecular solids would be ice. Okay, the second one, covalent network crystals. These are the coolest ones. Okay, this would be 100% covalent. When you see covalent network crystals, these are gemstones. If you have pure carbon, all black, with all 100% bonds, and I have models of these in the classroom always, but I don't have that would be a diamond. Okay, these are the strongest materials there are. Very hard, high melting point. Your examples are diamond. If I have silicon, SiO2, SiO2 is not just a single silicon with 2 oxygens. It's actually a repeating structure of Si and O. And it just repeats forever. And you would see that as glass, okay, or sand, silicon dioxide. If you melt it, it just kind of polymerizes, which means it just keeps repeating in every direction. Okay, the gemstones that are based on silicon dioxide would be like amethyst or citrine. Uh, if it's totally clear, um, yeah, that's really good. That would be called quartz. And when you see all the different colors of quartzes, it's because you have entrapped transition metals with color. So like iron would give citrine its kind of orangish color or yellowish color. You had Mn, manganese, that would give amethyst its purple color. So these are like semi-precious SiO2. Um, Other types of covalent network crystals, if you have aluminum furniture and it oxidizes, the interesting thing about aluminum is aluminum oxide is a covalent network crystal. So it actually becomes like this network that protects, like a patina, that protects the inner aluminum. So that's why aluminum doesn't just totally oxidize real quick. It forms aluminum oxide. That's called bauxite. If you find it on an island, like that's the ore for aluminum oxide. And aluminum oxide is really how you get rubies and emeralds are based on aluminum oxide. Um, and corabundum, corabundum. Used to be able to buy that as a sand, and if you actually look at the particles, you can see like little red ones because you get little sapphires in it that are like not that valuable. But this is used for sandpaper. It's not as it's not as strong as a pure diamond. So usually in sandpaper they use corabundum. And the interestingly enough, when I was in the epoxy business, we used diamond chipped blades. We would actually take saw blades and have them embedded with diamonds to cut through something really hard like epoxy. Okay, ionic, that would be cations and anions, metals and nonmetals. So the difference between like covalent network and ionic, you put covalent network in water and it won't dissolve. Well, the reason you can't use ionics for gemstones is you put them in water and they come apart. That becomes an ion dipole force, where that covalent bond won't separate. Okay, and then the last one is metallic bonding, and I really haven't talked about metallic bonding, but if you had a bunch of atoms like gold, there's a force that holds all your gold atoms together. That's metallic bonding, and we haven't done quantum theory yet, but if you look at the structure of the electrons, what holds it together, the secret to the force, is the outer electrons in each atom all become one. So it becomes this force of electrons holding it together, and that's metallic bonding. Since it has electrons, it's able to conduct electricity. Okay, covalent network would be non-conductive because the electrons can't flow. Ionic is non-conductive if it's in a solid. If you melt an ion, then it can start moving, and so ionic will conduct if it's melted, or if you put it in water, and the particles then become free to flow. Molecular does not conduct, and metallic does conduct because his outer electrons can be shared. Okay, they can pass through it. All right, that's types of bonding in crystalline solids. There's a little model of ionic. Not a great model. Covalent. This is what we call the sea of electrons. There's a sea of outer electrons that flow, not held in place. And then molecular bonding would be like hydrogen bonding. Okay. Phase diagrams. I think I've talked enough about phase diagrams. Solid, liquid, gas, triple point, critical point, supercritical fluid above there. Supercritical. That's why it kind of just blends into itself. This one would be a normal. Most things are more dense as a solid than a liquid. So this would be like, this one's almost linear. There's almost very little change between solid and liquid. But most things are forward like that. this is water down here. Water is the only one where you get a backward slope because the liquid is more dense than the solid, and that's fortunate for us because when you have like an ocean freeze, the ice always floats. If the ice sank, you could get it would probably kill all life because your ocean would become frozen from bottom to top. Okay, and luckily for us, if you go on the bottom, all seawater, the most dense that water gets is 4 degrees Celsius. So usually if you go in deep water like 6,000 degrees, if you go down to the bottom, all the water is always 4 degrees Celsius. That's the most dense it gets. And that's why if you experience going in the beach in the early spring or early summer, you dive down and you'll discover there's a line that's called the thermocline. We get warm water on top and the dense water on bottom, and suddenly you're in almost freezing water when the water on top can be like 70 degrees or 74 degrees. Okay, um, that's that. I made this little chart. Um, I'll just do one of these. Comparing substances. F2, Cl2, Br2, I2. These forces are all LDF. So the type of force is LDF. LDF. Now, magnitude. The light one is low, and the heavy one is high. Now, all these forces, these are properties, right? So vapor pressure. Vapor pressure, if you have a low magnitude force, you get a high vapor pressure. You get a low vapor pressure if you have a low magnitude, if you have a high magnitude force. Okay, well, boiling point's the exact opposite of your vapor pressure. If you have a high vapor pressure, that leads to a low boiling point. A low vapor pressure leads to a high boiling point. Now, melting point would be the same as boiling point, low, high. Now, if I start going through all my forces, the biggest thing is this magnitude force being low makes your viscosity low, makes your surface tension low, makes your capillary action low, and your delta H is low. And again, if this magnitude of force is high, this is the same for everything. High, 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 high. Okay, so these are your properties. And your properties, the main thing about it is your properties are related to your forces, your intermolecular forces. These are all hydrocarbons, and so they're all LDF. Okay, the magnitude of force, the heaviest one would be high, the lightest one would be low, and you get the same thing.